to do is that, so now, first of all, thank you very much for coming back. It means a lot. The second thing is that if you got lost, maybe, then basically the remainder of the talk is basically to introduce a commitment scheme, like actually what this commitment is, and also a way to prove quadratic relations over the ring. Okay, so that's basically what's there left. Okay, so let's start with a commitment scheme. Okay, so the commitment scheme is a combination of the classic cis commitment or cis commitment in this case, together with the BDLOP commitment. Okay, so let me explain slowly what's happening. So suppose I want to commit to a polynomial vector. Okay, so everything is over the ring, and I have my message consists of two parts. The first one is S1. And I will, if you want to keep the context, then I will say S1 is my S. Okay, this is the binary, the binary vector thing. And my M will be Y and G. So basically this, this irrelevant, somewhat irrelevant parts for me. Okay, and I assume that S1 has small norm, but M can have large norm. It can be arbitrary large, ring elements. And this is the case for G exactly, right? Because when we had this, that was long further away. Here, I literally pick uniformly random polynomials, right? So the norms of these can actually be big. So I will put those exactly in the M part. Okay. And now what is the commitment? The commitment is the following. So it consists of two parts, the TA and TB. So what is TA? TA is A1S1 plus A2S2, where A1 and A2 are uniformly random matrices. Okay, so I have A1S1, A2S2. That's TA. And this is, if you put S1 and S2, S2 is my randomness. I will sample randomness S2. So yeah, if you just look at TA, then A1S1 plus A2S2 is exactly this cis commitment that we had in the previous lecture. Okay, so that's, binding and so on, kind of similar thing. Then we have the second part, which is TB, and TB is equal to BS2 plus M. Okay. And yeah, so like the first clear observation is that if we have S2, if I have the randomness and I know the commitment, then I already know the M, because TB is BS2 plus M. Okay, so the commitment has these two parts. So one is the I type, second one is kind of similar to this BDLOP commitment scheme. Anything? Right. So yeah, so for people more familiar with the commitments, if L is equal to 0, so what was L? L is the length of the big message M. If L is 0, then we have I type. So basically TA is A1S1 plus A2S2. Simple. And then if M is equal to 0, then you get, that's exactly the BDLOP commit. Right. So yeah, so we have this distinction between messages. We split the message to the one with small norm and the one with big norm. Are there any questions so far? Yes.
Is this better than using just the BDLOP commitment?
Yes, because in the BDLOP commitment, yeah, that's a good question. In the BDLOP commitment, your M would be S1M. So you would have S1 in the part below. And because, TB is equal to BS2 plus M, which means that the length of the size of TB is the same as the size of M. And now if you have S1 being here, then your TB also grows.
Like you have a commitment that's like compressing over things with small norm and then binding over arbitrary things.
Exactly.
But
yeah.
then it grows linearly.
Right. So the goal is to commit to these big things, not many big things, but all the things with small norm you put in the top part. Yeah, good. Any other questions? Okay, so like, you know, if I want to say, okay, what about binding, for example? So the binding, if you just ignore TB, I have TA, A1, S1, A2, S2. So we know that in that part, it must be binding, right? Because it's just cis, right? And then if I have two, you know, like two commitments, like two openings with the same randomness, then as I said before, the message is determined directly from the commitment and the randomness. So this means that, yeah, so that's basically the binding property. And the hiding, you know, you pick randomness long enough so that this term is pseudo-random. Any questions about binding or hiding? Let me check if there are. Oh, right. Okay, so breaking binding implies finding a solution for A1, A2. And then, yeah, hiding comes from this part if that's we want to use. For example, using the LWE or like using statistical argument if someone wants it.
Is B the randomness here, or?
Yeah, so B, yeah, A1, A2, and B are like random matrices.
Yeah.
Disclaimer, this B is different than the B for approximate range groups. Okay, is it clear? This is
why was only the it didn't go back to the binding?
yes.
Because, yeah. Why does the lower part not play a role? Because I mean I'm committing to S1M, no?
Right,
So
right.
If I keep the S1 but choose a different M,
Exactly.
which
So
it works, then it's also break binding.
so the thing is that S2 in you know, if you come up with two openings, you know, this you know, this sentence means that I must have the same S2 for those two openings, right? And the thing with M is that M is determined by TB minus BS2. So if S2 is the same and TB is the same, then we have the same message. Yes.
But then the TB part isn't binding on its own, right?
On its own, no.
Didn't you say that was just a BDLOP commitment?
The BDLOP commitment is where you, I mean, for the BDLOP commitment, you will have this part. So then you do binding here. Yeah.
And how are MSIS and MLWE, how are they related? Or like, do they reduce into one another?
I mean,
Or is it like two separate assumptions that I'm making here?
I mean, they are related. Like, you know, the common denominator is some kind of, you know, shortest vector problem.
Think of it as decisional and computational diffie-Hellman, but for lattices. And hard to find, and one is hard to distinguish.
Okay, so this is the commitment scheme, and as I said before, just keep in mind, my S part I will put in S1, and there were these parts like Y and G that we don't really care. I put that in the M. Okay, so what I will do is that, yeah, I commit. Okay, yeah, so maybe one interesting part is that at least for the bottom part, for TB, if I, you know, I can start with the commitment, which is TA. Okay, what I do is I first commit to S1. Okay, so that's my TA. But in the meantime, I told you, like in this in this figure here, I start sending commitments, this commitment and this commitment, this commitment everywhere. Like at some point, I just send commitments. So the nice part about BDLOP, and here it's kind of inherited from BDLOP, is that I can, you know, add more rows every time. So like I have this M, and then what was that? I commit to Y. Okay, I add a new row. I commit to G. I add a new row. So this is, you know, like I can always update this commitment. And this is, yeah, this is important. But then there was this question, when I commit to stuff, do I need to use different randomness or like the same randomness? No, I will stick with S2. So my randomness is always S2. And I just add new rows to this commitment.
B then becomes larger.
Yeah, exactly, yeah. So the hope is that you don't need to commit to many bottom row.
Know how many?
Yeah, I need to know in advance how many.
Sixth, right?
Yeah,
So
yeah. Okay, so yes,
One
you
question.
yes.
Forgot what is capital B, it's a binary, right?
Sorry.
Capital B is binary.
Capital what, sorry?
Capital B,
No, yeah, exactly. So this B is a random matrix over the ring. It's not the same B as in the approximate range. I can only use that many letters. Yeah, I was hoping that you would forget after the lunch. Okay, so what did I promise here? I need to prove knowledge of the opening. So let's do this. So first I will prove knowledge of the opening, and later on how to upgrade it to prove quadratic equations. One quadratic equation, and then we are done. So congrats. Okay, so actually proving, so what's going on? I want to prove that I know S1 and S2. I actually don't need to prove that I know M, because M is derived deterministically from S2. I just need to prove that I know S1 and S2. I mean, yeah, I can prove that I know M, but this won't appear anywhere, basically. So basically, I want to prove that I know, the secret information here. Okay, and because as I said, if I know S2, I know M. I literally ignore the bottom part. So I ignore the bottom equation. So basically, what I do is I prove that TA is equal to A1 S1 plus A2 S2. And then you are like, I mean, you can imagine, wait a second, but isn't it something that we started with? And it's all, 1 hour wasted. So the thing is that here, what I will show is that I allow myself here to have an approximate proof. So exactly, so here I can do it, but later on I will, all the other steps will make sure that I at the end I get an exact proof. Okay, yeah, so let's just the same protocol as what Lisa had, literally. So basically what I start with, so I want to prove that TA is equal to A1 S1 plus A2 S2. Okay, so I send this part, the W. So I sample yi's. I send the W equal to A1 Y1 plus A2 Y2. The verifier picks a challenge, and I send all the masked opening Zi equal to Yi plus CSI. In particular, yeah, there should be rejection sampling, but let's ignore that in this talk. Yeah, and then the verifier checks that Z1, Z2 are short, and A1 Z1 plus A2 Z2 is equal to W plus CTA. Okay, so literally the same protocol as before. Are there any questions? Yes.
Confused about the fact that you don't prove anything about N. So this is not useful for saying anything about N.
So basically, what I will say is that it's interesting. So the thing is that I want to prove knowledge of S2, and M is derived deterministically from S2. Okay, so like prove knowledge of opening is only this way. Like I need to only prove S1 and S2 because M is derived deterministically. But later on, if I want to prove some properties about M, then it comes in. Yeah. Good question. Any other questions?
Would you still do rejection sampling here?
Yes.
Do we not care at this point that we have a multiple of S2 and not but S2 itself is small?
Yes, exactly. Oh, S2 is the randomness. Yes, we don't care about that as long as we ensure some kind of binding. So this is the part, long time ago, 3 hours ago, Lisa mentioned something about the fractions being unique. This is the part, yeah.
Just to quickly reiterate, what does the verifier now know at this stage, like after running this? What is the information the verifier now can be convinced of?
The verifier is convinced that the prover has a approximately valid opening. You remember, like for approximate, there was the C times blah blah blah. You will get.
I know that you have an S1, S2, which is small, such that A1, A2 times S1, S2 is TA times some small gamma.
Yeah.
Okay.
Yeah. Makes sense. For now, yes. I mean, we'll go.
We don't know the concrete values, you just know that they are short and
then there's
they
some
correspond to this commitment.
Yeah, approximately. So how many people are still following? Okay. Good. Okay, so yeah, so with the soundness argument, we'll come back to it, but let me just focus on proving quadratic equations. Okay, so in general, we would have something, very ugly stuff, but for the purposes of concreteness, I'll focus on this very simple quadratic equation. Okay, so what do we have? I have some short message S1, I have some message M, and I want to prove that S1 transpose S1 plus M transpose M is equal to 0. And like very, like you wouldn't do this, in some concrete applications, but just want to give an example how you would proceed. Okay. But yeah, like proving general quadratic equation, which we wanted to do here, it will be the same strategy. Okay. So how do we prove that? So we have this sigma protocol, which was done before, right? Okay. So yeah, so I guess yeah, this technique is kind of similar to the Vol presentation actually. So so the verify gets all the zi's, right? So if I multiply Z1 transpose Z1, I mean, why would I do that? Well, let's see. If I multiply Z1 transpose with Z1, then by writing it out, if you look at this as some kind of quadratic equation over C, then the quadratic term has this part we're interested in. Okay, so our goal will be to somehow come up, with some expression where the quadratic term is exactly that part. And we will prove that the coefficient of this quadratic term is equal to 0. Okay. So, this is just, I just wrote down this statement. I mean, this holds, right? Okay, so now slowly, like I could try to do something with M because I want M. I want M transpose M, but I don't have anything here, literally, right? I mean, there's no M here. So then what do we do? So now we're using the fact that if that given S2, I can compute M. Okay, so M is derived deterministically from S2. Okay, so exactly, I will use the following property, that TB minus BZ2, where Z2 is Y2 plus CS2, is equal to minus BY2 plus CM. So this equation here is derived exactly from the definition of M at the top. Okay, because what is is it correct? So TB. Let me double. Yeah, I think there's a typo. It should be CT. It's a CTB because TB is equal to BS2 plus M. and I multiply C times TB. So it's a C times BS2 plus CM. Okay. And then I use that Z2 is Y2 plus CS2. So how many, okay, so let's check in the interest of time, how many people are interested in deriving this calculation? Okay, I guess we can quickly do that. Oh, right. Yeah. Forgot. Okay, fancy.
Is it just me?
Right, so this should be like, I don't.
No, it was not working yesterday.
Oh, really?
But I can see the C.
Yeah.
Oh, yeah.
Oh,
Okay, so CTB is equal to B times CS2 plus CM, right? And then BZ2 is equal to BY2 plus CM. Oh, sorry, BZ2 is BY2 plus CS2. BCS2. It's okay, I can remove stuff. Okay, and then yeah, if you subtract, you get that. Okay, so the idea is that if I multiply this term and use this property, then I do get a quadratic equation where the quadratic term is what we wanted, right? So M transpose M. Oh no, is this typo gonna propagate? Probably. No. So this means that if I combine these two observations, I do end up with some quadratic equation where this quadratic part is exactly what I wanted to prove it's zero. Okay, and then there are all these like linear terms which we don't care too much. And the part on the left can be exactly derived by the verify itself. Okay, so what I'm gonna do is I have these terms G0 and G1, so I can commit to it. So what I will do is that I commit to this G1 and I append the row to the bottom. Okay, it's still a valid ABDLOP commitment. Okay, so I commit and then what do I do, right?
B0 and B1 is the same here.
Sorry.
You have B0 on the bottom and you have B1 at the up the right corner.
Oh, wait.
Same thing.
Yeah, it's the same thing. Interesting.
It should just be B1.
Yeah, it should be B1. Ah, wait, I can now correct.
So what happens is that he commits to the things that he wants to compute the product of, the inner product of, and then in his head he sampled like the prover receives a challenge, and then he computes these cross terms and also add those to the commitment. Right. So like the verifier hasn't received these at this point, right? He's gonna receive them at the end, or
Right, you mean like, for example, the G1?
yeah.
This is sent together with W.
Okay. Yeah.
This is independent of C. That's it,
Oh yeah. Okay. Yeah.
right? The G1, G0, G1 are independent.
Oh
of
yeah.
C.
Okay. Yeah.
And I will prove that, I will commit to some stuff and I will prove that, commit to everything apart from the quadratic term. And I will argue that this quadratic term should vanish.
Yeah.
Should it be clear at this point why we are committing to this T1? Because I don't see why we need
G1?
T1. Like why this value to which I commit there? So I don't see why
You'll be committing to G1, right?
we computing with T1 and
Yeah.
adding it there and
Yeah.
the B1 of the B1. Like why?
Adding it up.
Like I don't see.
The idea is that I have this quadratic thing, right? And I want to kind of, technically speaking, give commitments to the constant and linear term to prove this quadratic equation without the quadratic term. And then this means that the quadratic term must be zero.
I see.
And what is B1 then?
Yeah, so it's like another, I take another random vector from the commitment. So now my my old matrix B is now B and B1 transpose. It's append. This has this nice this BDLOP commitment has this nice property of appending.
This follows from this, what we just discussed.
Yeah.
The property of this commitment scheme that you can somehow enforce this while adding it kind of. Oh, yeah, so just said, okay.
Yeah, yeah.
And the goal is then to prove that this equality there holds just using the committed values for B1 and
Yeah.
B0.
Yeah.
Sorry, although it doesn't matter a lot, but should Z1 transpose Z1 equals to there is a Y1 transpose S1 and S1 transpose Y1 rather than two Y1 transpose S1. The middle term, 2C Y1 transpose S1. Should it be C Y1 transpose S1 and C S1 transpose Y1?
I mean, yeah, but the transpose is the same, right? Y transpose S is the same as Y S transpose Y.
Inner product where you change to.
Oh, okay.
In the product.
As long as they're vectors, that will be true.
Okay, so I have this T1. So now if you want to remember what T1 was, I put it up there. So let me just continue. Okay, so now so what's going on? So I guess I have this okay, so what I'll do is I have this term. I can use this term is the same as here, right? This is the same as this. Okay, and I will append, I will subtract this part. Okay, and then actually this part, as we derived in here, the same technique as before. Oh yeah, C. Everybody's missing C. This can be equal to B1 transpose Y2 plus CG1. Okay, so like this equation I wrote is exactly the same as this calculation I did. The same, literally. Okay. Okay, so now subtracting this allows me to cancel out CG1. So I get this part. Where the right-hand side doesn't depend on C, right? So that's nice. Okay, so maybe to see kind of the motivation instead of just writing random equations, let's look at the protocol. Okay, I want to prove this quadratic equation. So there is, okay, so I start with the opening proof as before. And now I compute all these terms, all the G0, G1 as we did before. Okay, so I do G1, I compute G1. I commit to T1. And my V is exactly G0 plus B1 transpose Y2. Okay, and what was G0? G0 is this term. Okay, so G0 plus B1 transpose Y2 is exactly this ugly term. Okay, and then I send this information. The verify gives me C, and I send the Z equal to YI plus CSI. Okay, so the black part is literally just the opening proof. Now I'm appending a lot of other stuff to prove quadratic equations. Okay, and then the verifier now checks that, that's the same as before, proving that ZI's are small, are short, A1 Z1 plus A2 Z2 is equal to W plus CTA. And all, another C. Yeah, I need to update that before I send. Yeah. So this is exactly this verification equation we had before. So. Okay, so this equation is exactly this equation at the bottom. Okay, so how many people still fall away? We have a few hands, more or less. But yeah, I would say that the like the main takeaway is kind of try to derive, like to look at the opening proof and try to derive things using the sets and the commitment to come up with this quadratic equation in C. With the equation you want to prove. So that's the takeaway.
If you have more complicated quadratic equations, then is there a general construction methodology, or do you have to construct this and find the formulas for each individual quadratic equation you want to prove?
I mean, if you make it general enough, then you can find the formula, but it would be just very ugly.
Okay, but there is a general construction methodology to do it, or
Yeah.
so I can prove arbitrary.
Quadratic, yeah.
What's the plan? You just take like this blinded version that falls out of the opening proof and you compute the entire quadratic equation and some insane number of like cross terms falls out and you commit to all of those.
Yeah. Basically.
Okay, yeah.
Basically.
Okay.
I mean, yeah, it's gonna be much uglier than this, right?
Yeah.
This is already somehow completely unintuitive, and then yeah, if you have general quadratics, and
I mean, here it was like this G0 and like this G0 and G1 here are not related to the G0 and G1 we had earlier.
no, these are just some garbage terms that I use for the quadratic. So yeah, you can believe that this way you can build quadratic equations, prove quadratic equations, and that's basically, oh, we're not done. Almost there. Right, so I promised quadratic equations with automorphisms. Right. So to prove that, we pick a challenge space for which sigma of C is equal to C. Am I gonna have this right? So this was, if I try to do the same kind of intuition, like the same idea as before. So I want to compute this term, but with automorphisms. Then obviously if I figure out the equations, I end up with terms which are C and some terms which are sigma of C, right? So there are some C, there are some sigma of C, there's even C times sigma of C. But now if I assume that the challenges are stable under the automorphism, then I end up with the same argument as before.
What was the challenge space here?
I haven't defined yet. So I define my challenge space to be stable under sigma. And then if I do this equation, which has, some parts are just polynomials, some parts are polynomials with sigma. If I look at this equation with over C, I still end up with a simple quadratic equation, right? Because there are some terms with sigma of C, but sigma of C is equal to C. So yeah.
You also need the requirement that C is invertible, like all of the challenges are invertible.
Yeah, later on, yeah. Later.
Or even right now.
I mean, I will, in the next slide, I'll discuss that, yeah. So complicated, yeah. So for the challenge space, we need, we want to have, we're working over the rings. We want to have a large challenge space, right? And also we want, sigma of C to be equal to C. Okay. And also we want the difference of distinct C and C prime to be invertible over RQ. And I will say why. You have a question now?
No.
Okay. So what I'm just gonna manually construct such a challenge space. So what can you see is that I have a constant term. I have the first half, which is whatever. And then I have the second half, which is the negation together with reverse. Okay. And this allows me to, you can manually check that for every element of, of this form, sigma of C is equal to C. Just, yeah, you can manually check that. Okay. In terms of like the challenge space, I still have like D over 2 degrees of freedom. So if I pick like, challenges with coefficients between minus kappa and kappa, I still can get some exponential challenge space. Okay, yeah, and this is like some argument why sigma of C is equal to C. And then we also prove in the paper that, if Q is 5 mod 8, then if C is non-zero and is stable under the automorphism, that it's invertible over RQ. So this gives some kind of a field, property.
Is that a unique value for Q, or is it just a useful one?
You can be 5 mod 8, that's it.
Yeah, but like, could it also be 3 mod 7 or whatever else? Like,
yeah, if it's, if it has a different structure, then I don't think this holds.
This is essentially equivalent to saying that you are using it to split in.
Yeah, yeah.
Okay. And it's not the only Q you can choose for to split in case of.
I mean, you can try to do, split differently and then use some other result that's, short elements are invertible.
Ah, okay.
But here you don't even talk about short elements. Right.
So the kappa, the fact that we choose small, that's only for completeness, basically. Like that when I multiply up this challenge by something, it doesn't blow up the norm, or
this kappa here, right?
yeah, the range from which we're choosing are.
Right. Yeah, you want these still to be short.
Yeah.
But you want them to be big enough so that the challenge space is exponential. Okay.
If Q is not of this form, then you would just have to check that the challenge is always invertible in RQ, or?
Yeah, there are some other results which say that, if a ring element is short, then it's invertible. There are some like more general results like that, which you could also use here. Okay, just continue. Yeah, so then to extract, we get 3 different because we deal with quadratic equations, we have to extract 3 different ring elements. Yeah, compute the inverse van der Monde, so basically the same as before. Okay, and then I'm stating this fraction lemma that Lisa mentioned. So, but this is now in the context of APDLOP. So what I'm saying is that, at above, this is exactly the approximate proof that we had, a few hours ago. And now, yeah, the lemma says that, if I look at this fraction, this is kind of what we want, right? Like if we do, let's say if we do Schnorr, we have this fraction and this is our witness. In this setting, we can't say it's our witness because it's not short. But I will, like my wishful thinking would be that this fraction is exactly my witness. Okay, but at least this lemma says that my candidate witness is unique, or we solve this. Okay. So yeah, so like this is just the same, the same lemma as before, but like in the context of APDLOP. Any questions?
This sounds like everything follows from cis, no?
Right.
So is it
yeah, it
it
follows
that like actually needs this extra property that the fractions are the same, then it's based on cis.
I mean, if these fractions are not the same, then we can solve this. This means that either these fractions are the same, or we solve this. Sorry?
I mean, like when the fractions are the same, we're not based on cis. Like Like the security doesn't reduce to cis or not. Then, because it could always be that the fractions are the same, no?
Yeah, yeah. So what I'm saying is that, okay, so look at this approximate statement above, okay? Divide by C star. Divide by C star. Then your wish would be that the original S1 was S1 star divided by C star. It's my wish. Obviously, we can't really deduce anything because first of all, S1 star divided by C star is not short, or in particular, it's not binary. We don't know anything about it. But I will call this my candidate witness. And then this lemma says that if you manage to to get different different kind of whatever like witnesses, then my candidate witness is always the same, or I solve cis.
Then it's statistically binding, and then you don't need a computational assumption.
Right. Yeah, if we manage to get this without the assumption, then yeah, it's binding. Okay, and this is like a very key property because yeah, we have this, we have this 3-round protocol, but on top of that, we have like a lot of building blocks. And then when we do reduction, we want to make sure that my candidate witness is always the same. Yeah. Okay, so like like from this 3-round protocol, we can extract the candidate witness, which satisfies all the properties. But then I need to prove that, my S1 was exactly, S1 has binary coefficients. Basically what we wanted to prove at the very beginning, right? So now we're going from bottom up. So from the opening proof, from these approximate proofs, I get a candidate witness, okay? From quadratic equations proving constant terms and so on, I get that my candidate witness satisfies all these algebraic relations. It's still big. It's still big, right? Okay, but it satisfies all these linear relations. But also the approximate range proof makes sure that the norm of S is somewhat small. So now this part does make sure that S is somewhat small. Okay, and then using basically our approach from the top to the bottom, we can deduce that S had binary coefficients.
There's still like a slack factor.
So this
S is actually a fraction.
Yeah, S is a fraction. It's big. It's like you can't say anything about its norm yet. Like from the first bullet point, you can't say anything about its norm.
You're saying the approximate range proof
Allows you to deduce that the norm of S was somewhat small.
I thought it allows you to deduce that the numerator is small and the denominator is also small.
Sorry.
The fraction.
Yeah. The fraction is also a vector, right?
Yeah, but I thought the approximate range proof doesn't tell you anything about like if you actually were to divide it out, it doesn't tell you.
No, like exactly the approximate range proof. So the one with the with this probabilistic test, there we had this argument saying that if S was big, then BS plus Y would have been big. But we know that BS plus Y is short, which means that S must have been short.
I see. Okay. Like when you say B, are you talking about the
Oh yeah, the approximate range proof B.
Oh, okay.
Can you remind me why the second bullet point is not sufficient to conclude that S was binary already?
Because from here you can't deduce that this holds over integers.
Right.
I'm a bit confused by the first thing. So we get the candidate witness somehow, but this means we don't really get it, right? Like it's
I mean, you extract something. That's true. But the question is, you need to you want to prove that what you extracted has exactly binary values. Let's say. That's why all this, all these steps above the 3-round protocol ensure all these properties here. So from the, from the 3-round protocol, I have this first bullet points. And then, from these quadratic
It
equations,
was like this friction, or like this something that,
I mean,
like this friction is not small.
exactly. I didn't say anything about small. This is just a big candidate with.
But then you say like that we're proving that it's small.
Oh yeah, because this is
This is like, but in the beginning it was big. So.
yeah. Because this approximate range proof makes sure that if S was, that was like at the very beginning of the talk, right? If S was big, then for random B, BS plus Y would also be big.
We got the S, we didn't got the BS plus Y, no?
Oh, we did. Let me just go back to, maybe it's just easier to.
So the candidate witness is BS plus Y. Or?
No, the candidate witness is S. Okay.
Exactly.
Yeah.
You said that S is large.
Yeah. If S was large, BS plus Y would be, I mean, yeah, what was that? If S was large, BS plus Y would also be large. But I sent you BS plus Y. So you can manually, the verify manually checks that BS plus Y is short.
The final slide you showed is kind of like we combining multiple facts and then we kind of combine multiple things we obtain along the way.
I'm just confused by this. I obtain the candidate witness and then it's big. Like I obtain a thing that is big, which I can check.
It's not big, you just don't know if it's small, right? The other part of the proof is just guaranteeing that what you extract.
So I'm not obtaining a vector that I can somehow check for smallness or something, but I'm like, what am I receiving? When you say like you obtain the candidate witness, what am I actually obtaining? What is the object I'm having that can
So imagine the extraction strategy, okay? In the extraction, you rewind the, you rewind the protocol and you end up with some candidate witness. And then if you don't, if you don't do any argument above, then you can't deduce that it has binary coefficients. And that's why all these intermediate steps in the first half, we need to introduce to kind of make sure that candidate witness satisfies all these terms. Constraints.
the extraction process, like the hypothetical witness that I would obtain if I do it, then okay.
Okay, thanks. Yeah. So when I say about candidate witness, it's about when proving knowledge soundness. Yes.
So just to be like super precise, like if you go back to the most recent slide.
This one?
Yeah. Okay, wait, so when you say approximate range proof, like this thing consists of both checking some quadratic equations, or like the approximate range proof went into the quadratic equation.
Yes.
And checking that this Z value is short.
Yes.
It's like both bullet 2 and bullet 3 are the ones that need to guarantee that S is small.
Right, because you want to prove that BS plus Y was equal to that Z, which is short, right? So proving BS plus Y went to this part.
Actual order of 3 components. Do you need to first to approximate proof and then precise proof for the other one?
Yeah, I think it's just easier to start with with approximate range proofs.
Yeah.
Then you end up with like proving linear inner products over integers, which then you move on to proving constant terms, which then you prove quadratic equations, and then you prove one single quadratic equation. Okay. Yeah, so maybe I'll leave the maybe like 10 minutes, so let me just maybe switch to the second talk very quickly. That's interesting. But yeah, so I think that basically it's kind of done. Now, yeah, which D to pick, challenge space, exponential challenge space, efficiency, but yeah, you can see the benchmarks are like top of line. Great.
It was have been a question, like, how efficient is it? Like,
Right. So if you want to prove like let's say the lattice statement equations, then actually like at least if I pick, favorably some nice parameters, then actually you can get, around 14 kilobytes per. Obviously it's not as good as the lithium, which is like 3-4 kilobytes. So it's really a back factor of 3 or something worse. But yeah. Yeah, I don't think like an improvement by a factor of 2 is possible in the lattice setting, unless there is some like very good new technique.
Sorry, so what is the advantage now compared to the lithium? Sorry, I didn't quite
So the lithium is just like if you take the protocol from the lithium, not just the signature, you prove this approximate. So you prove AS is equal to gamma.
Okay, now we went from a
Now we're proving
exact.
exact
Okay.
stuff.
Yeah, yeah. Okay. Yeah.
Binary proof.
Just need to be reminded of the whole point. Okay. It's been a while.
Yes.
So if you get this gamma approximate proof from dilithium, what was wrong with with using that instead of your random B times S approximate proof?
Sorry, what was the question?
Well, so you have this proof where you do the inner product of this B and this S to do an approximate range proof. What was the problem with just using dilithium instead?
So with dilithium instead, you would you can't deduce that your candidate witness is short. You will still end up with if you do the lithium there, you'd end up with a fraction.
Is that because like the gamma isn't invertible, or?
I mean, basically, it is invertible, and you can divide by gamma, whatever. But like this doesn't ensure that whatever witness you had was small. Does it make sense? Yeah.
So the exact thing, we get the exact the polynomial, because in the simulator you show that we either break his problem or you get the same thing. Is that why we get the exactness? Or
I mean, what you said is about having the binding property of the
yeah.
Because so it only shows that my candidate witness is unique. Because just imagine like in all steps there is a rewinding, like knowledge extraction. There is rewinding everywhere. And now, for example, if I rewind here I end up with some candidate witness. I rewind again, and then in another execution, I end up with a second candidate witness, second fraction. I want to make sure that all these fractions are the same. I always talk about the same candidate witness. But yeah, but if not, then we can like I guess move on to the second one. I'm not sure if there's much time, but Yep. Okay, let's see if I have time. It's a lightning talk, basically. Well, yeah, I wanted to do a quiz, but there's not much. Right, so just ignore the quiz. So the thing with so there is a scheme called Labrador, and that the protocol kind of uses all the techniques we had in the previous presentation. But the problem is that it uses approximate range proof to kind of argue shortness. Okay. And then the problem with this is that in this approximate range proof, if you remember, the verifier sends this challenge matrix with random 0, 1 entries, right? And basically this matrix has the same width as the length of the witness. So like just doing approximate range proof on its own will take linear verification time. So now the question is, how can we build succinct arguments where we can get some succinct verification? Okay, obviously the end goal is to get some snark, zk snark, which these can be built, using polynomial commitments and IOPs. But like in the lattice setting, even just commitments with a succinct proof of opening with succinct verification is difficult. So one can do the compressed sigma protocol and stuff, but then this also results in with linear verification. Okay, so yeah, so this is hard in the lattice setting. Yeah, so the next 10 minutes will probably be just the discussion of the square root construction. Okay, so yeah, that's the ITEC commitment. So as before, if I want to commit to a short vector S, I compute A times S with the T, and it's compressing. T is the commitment, and binding holds under cis. And yeah, right. And now, if I want to prove knowledge of this opening, yeah, in the lattice bulletproofs, the verifier somehow needs to, cut this matrix A in half and then, make operations on this A. And there were some approaches which either use some pre-processing or put some more structure to A, but then relying on new lattice assumptions. Okay. So in this talk, I want to, yeah, so I'll put the whole presentation. So I gave like a concrete example of a square root approach, cube root, and then how you can extend it to the polylog opening proof with succinct verification. Right. I mean, now it's going to be fast. So the goal is not like, yeah, it's, let's just continue. Okay, so the square root approach is kind of simple, and I hope I can do this in 10 minutes or less. I have this vector S, which has length m. Okay. Oh, and in this presentation, I talk over, everything is over integers, so no rings anywhere. Okay, so I have this S, and I split this S into square root parts. I mean, this was already hinted during Lisa's talk, actually. So I split this S into square roots, smaller witnesses, right? And I apply S to A to each of them. Okay, so I get AS1 up to AS square root of n. Okay, so I get my T's, and a commitment to vector S are all these T's. Okay, so the size is n square root of m log q. It's more or less square root.
You mean, do you split up A here? I mean, how does A match with the length of S1 now?
Yeah, I just pick A to have these dimensions.
Oh, sorry, yeah.
What is n here?
N is the dimension, the height of A, which will
okay,
determine hardness of cis. Okay. So mathematically, so can you raise your hand if you're more or less familiar with the tensor notation? Yeah, I have the next slide, but yeah, that's the next slide. So yeah, so mathematically, it's just, I take this S, and on the left, I multiply it with this matrix, where on the diagonals, I have A. So A. Okay. Okay, so that's the same thing. Okay, and it can be shown that, if you can find different short vectors S and S prime, then, if you get this equation, then you can break cis for the matrix A. Okay, any questions so far? Okay, yeah, so these are like simple properties of the tensor product. And yeah, I will mostly use this part, the mixed product property.
We're talking about a different set of parameters now for the cis problem that we were originally considering, right?
So you mean like compared, like this tensor cis commitment compared to the normal?
We started big A, big S. And now we've broken up A, we've broken up S.
Right.
These instances on their own, are we relating it back to the original SAS instance, or are we considering individual smaller parameter SAS problems? Like the blue A and S1, for example. You're talking about that as an SAS instance?
Well, I'm talking about SAS for this A. Right, so if S and S prime differ, it differ for one of those instances.
Okay.
And I can find a short solution for A. Okay, and now what's the opening proof? So I want to prove that I know some short S such that this holds. Okay. So because we don't have zero knowledge, so this has nice property that we start from the verifier basically. The prover has nothing to send. Or you could think of the first message to be the commitment which is sent. Okay, so the verifier sends the C. So what's going on? The C is a binary matrix which has kappa rows, and kappa will be used for soundness, and the width is square root of m. Okay, and Z, what I do is that I compute Z equal to C transpose identity times S. Yeah, this may look like magical, but from completeness, we'll see why this happens. And then the verifier checks these equations. Okay, so let me just go through the first one because like there are some tenses around. I understand if it's not intuitive. Okay, so what I do is that the first, you can see the mouse, cool. Identity times A times Z. Okay, what is Z? Z is this, right? So I get identity times A times C tensor identity S. Okay, so I just substituted, right? Then I'm using the mixed product here and here. And I use the fact that identity times C is the same as C times identity. Okay, which allows me to get the second equation. Okay, and I know that whatever I have on the right hand side is just T. Is it somewhat clear? Any questions?
Basically, the approximate range check applied to every component.
Basically, yeah. But the nice thing here is that, well, is it a nice thing? Yeah, it is kind of the same as the approximate example with challenge space 0, 1. But now I can show that this protocol has negligible soundness error. And this is what the kappa is used for. Okay. Yeah, so like if you compute the sizes, then you get square roots. So to prove this thing, yeah, 5 minutes should be enough. We will use this property which we call coordinate-wise special soundness. Okay, so we have this special soundness, so that's what we already had, where given two valid transcripts with two different challenges, I can extract the witness. Okay, for coordinate-wise special soundness, I need the property that C is some form of a vector. Okay, so here I assume that C is some vector of T coordinates. Okay, so if C is some vector of T coordinates, the coordinate-wise special soundness says that if I'm given T plus 1 valid transcripts with the same first message, but different CIs, and then different ZIs possibly, such that which have the following form. So C0 is the first, the challenge from the first transcript, and I have T coordinates here. And then C1 differs from C0 exactly in the first coordinate. Okay, and then everything else is the same, but the first coordinate is different. Okay, I have C2, which differs from C0 exactly in the second coordinate. Okay, and so on until I have CT, which differs from C0 in the T coordinate. Okay, so if I am given this type of challenges, then I can extract. Okay, so this is kind of some kind of generalization of special soundness. So this gives you special soundness if you only have, if T is equal to 1. Yes.
The transcripts don't have to come out in that order, right? It's not the prover's stateful somehow.
Right, when you rewind, right, like it's not necessary for the first one, for the first to be like the main one, I guess. But yeah, it can be any of those. I just need one, like a one main one, and all the others different from that one. Yeah, so there's this result that, you know, like if you have coordinate-wise special soundness, then you get knowledge soundness. You know, with the problem with error t divided by this size of the space of one coordinate. Okay, so in our example, I will look at C to be a vector of square root of m coordinates, where each coordinate is a binary vector of length kappa. Okay, and in this particular setting, the size of S would be 2 to the kappa. So we get negligible soundness error. Okay, so let's just prove coordinate-wise special soundness. I guess will be done. Suppose we're given, you know, let's say I focus on the, you know, the jth coordinate. Okay. So suppose I have two matrices C and C prime, which differ in the jth column. Okay, and exactly in the jth column. So in all the other columns, they are the same. And suppose that Cij is not equal to Cij for some I. Okay? Because they are different in the jth column, right? So I can pick such an index. And then for each j, I will extract a short as j star, such that a as j star is equal to tj. And by, you know, combining for each j, I can reconstruct my S. Okay. Any questions? I mean, yeah. So that we can collect from all the SJ stars to get the. Okay, so I'm just gonna look at the verification equation. That's it, right? So suppose I have these two transcripts, C and Z, C prime, Z prime, and I can, this Z, I can write Z as, a vector. I can just parse it as Z1, Z2 up to Z square root of M, and the same for Z prime. And then from the first verification equation, I, for some fixed I get these two equations. Okay. And then, yeah, similarly as before, I can just subtract these two guys. And because, these matrices differ exactly in the J coordinate, all the other terms disappear apart from the TJ. So I get this part times TJ. Okay. And then because I have binary challenges, this is plus minus 1. So plus minus TJ. Okay, so then by multiply, I get SJ star, which is short. Okay, so yeah, so maybe let's have a break. But yeah, so I give a sketch how to prove polynomial evaluations. But yeah, I'll just leave it in the slides then. Yeah, so I guess it's a good place to stop.